All right. Penelope. Who is Mike Hunt? I don't know who he is.
Yeah.
All right. Who are you? All right. So let's do this. So basically, we are going to do a more formal introduction to integration. All right. So this is what basically we will go through. All right. So first thing, the first idea is find the area of the region enclosed by the graph of this function over the interval from 0 to 8. So the function is the blue line, okay? And we want to find the area between the function, the x-axis, and the lines x equals 0 and x equals a. All right. So this is the idea. The idea is to break this up into pieces that are easy for us to calculate. All right. So the easiest way to do that is to actually create rectangles in this case. Okay. So we create 1, 2, 3, 4 rectangles. In this particular case, each rectangle has the same length as the base. So if you look at this, has a base of 2, 2, 2, and 2. Okay. It is, let's say, convenient, is what we usually will do, but it doesn't have to be that they have the same base length. Okay. So in this case, we just find the height, and notice that for this particular rectangle, the area will be 2, which is the base, times the function value, okay? And the function value in this case is 2. So this is f of x, which in this case is 2, right? So the area here is 2 times 2, which is 4, right? So, and we add that to the following rectangle. So the area of the following rectangle is the same base times the function value, and the function value in this case is 3. So it's 2 times 3, okay? Plus 2 times the function value, which in this case is 1. F of x is 1. And that is equal or the same thing for the last rectangle. So it's going to be 2 times the value of the function, and the value of the function in this case is 5. So we multiply 2 times 5. So we're going to have 2 times 2 is 4, 2 times 3 is 6, that will be 10, 2 times 1 is 12. So I'm sorry, 2 times 1 is 2, plus 10 is 12, and then 2 times 5 is 10, so it's 22, right? That's the area there. If we try to do the same thing for this particular graph, okay, then we can see that it's easier for here to split this up into these rectangles. And if you look at them, obviously they don't have the same base length, right? In this case, this is 1 times the function value, which in this case is 5, plus, in this case, the base is 3, times the function value, which is 2, plus 1 times the function value, which is 3. I'm sorry, yes, 3. And the last one is 1, 2, 3 times the function value, which in this case is 4. Okay? We add all that together, and then we have the area. And the area in this case is going to be 5, and 6, 11, and 3, 14, and 12, 26. Okay? So in both cases, what we have done is that we have done a partition of the interval that is given to us, okay? In the first case, the partition has the same length for the bases, okay? So we divided the interval from 0 to 8 in 4 intervals or even of even length, because they have the same length, all right? On the second example, we have a different partition and the lengths of the intervals are not the same, okay? So most of the time, we end up doing this because it's more convenient, all right? Which is meaning a partition where all the intervals or all the rectangles have the same base length. So that's what we're gonna try to do here, okay? So it says, while considering the process you took to find the area of the two regions above, try to approximate the area under the following curves and above the x-axis over the interval from 0 to 8. Now, notice, in here, we talk about finding the area, which means this area is exact. Those are the exact values. Why? Because these rectangles, the area are easy to calculate. While here, they're telling us to approximate, right? To approximate. So the implication is that we're not gonna get an exact value, all right? So if you notice, there are some points already in the curve. I'm gonna use those points on the first graph to make my estimation. So basically what I'm saying is I'm gonna use this to create my first rectangle. So my first rectangle goes from 0 to 2, okay? My second rectangle is gonna go from 2 to 4. The next rectangle is gonna go from 4 to 5. And the last rectangle, and the next rectangle will go from 5 to 6. Okay? And the last one will go from 6 to 7. So in this partition, they're not evenly distribute the length of the bases, right? Now look, well, I can build a rectangle by using either this height or by using this height, right? This will be the base, and I can choose either this point as the height and that point as the height. So which one should I choose? Well, there are two methods basically. Well, there is more than two, but we have two options. We can choose of this subinterval, from 0 to 2, we can choose the left endpoint, which will be 0. And from 2 to 4, the left endpoint, and with that, we will use this as the height. So basically what I'm saying is I could use either the left endpoint, which means I'm going to use this point on the first interval, I'm going to use this point on the second interval, this one on the third, this one on the fourth, and this one on the fifth, to determine the heights of the rectangles. So if I use the left endpoint of each subinterval, then these are the rectangles I'm going to get, because between 0 and 2, the left endpoint is 0, the height is there. Remember what we did up here. How did we find the area of the rectangle? The base times the function value. So in this case, I'm doing the left endpoint to give me the function value, okay? So for the first rectangle, the base is 2. So it's an approximation. So the base is 2 times the function value. The function value on the left endpoint is 2, right? Now, for the second rectangle, so I'm going to use, again, the left endpoint to determine the height. So the rectangle will go up to here. So for the second rectangle, the area is going to be 2, because the base, again, is 2, times the function value. Well, the function value here is f of 2, because I'm using the left endpoint, f of 2 is 3. So it will be 2 times 3. Okay. On the following rectangle, if I use the left endpoint, so the height is going to be here. So the rectangle I'm using is this. So for the third rectangle, the base is 1. How much is the function value? At 4, which is the left endpoint. The function value at 4 is 3. So it's going to be 1 times 3. Okay. For the following rectangle, plus is going to be the left endpoint. So my height is determined by 5. Is this rectangle. So the area of that rectangle is going to be 1 times f of 5, which is 1. So it's 1 times 1. For the next rectangle, this one, the left endpoint is 6. The function value is f of 6, which in this case is 5. So for the following rectangle, this is the rectangle between 6 and 8, right? The height is f of 5, so the base is 2 times 5. And then after that, I multiply this out and add it together, and that's an approximation of the area under the graph and the interval from 0 to 8. So it's going to be 4 and 6, 10, 13, 14, and 10, 24. Right? That is if I use the what? The left endpoint. Now, it's an approximated value. You can see that there are areas that I'm not including. Let's underline those with blue. So I didn't include this, and I didn't include that. I didn't include this piece, and I didn't include that. However, I included this, which is not even, is something that I should consider. But that's based on how I build the rectangles, okay? And that's why it's a what? An approximated value, okay? Now, if I want to use the right endpoint, the process is the same, only that the height of the rectangle is determined by the right endpoint of the subinterval. So I'm going to do that here, okay? So if I were to use the right endpoint to approximate this area, then I'm going to consider these rectangles. This rectangle, I'm going to consider this rectangle, I'm going to consider this one here, and this one. All right, those are going to be my rectangles. So the height of each rectangle is going to be determined by the right endpoint. Between 0 and 1, the right endpoint is 1. Between 1 and 4, the right endpoint is 4. Between 4 and 5, the right endpoint is 5. And between 5 and 8, the right endpoint is 8. Okay, so here is how we build the rectangle. So one rectangle is this. Remember, I'm using the right endpoint. The other rectangle will be this one, because it's the right. The following will be this. And the last one will be this one. And we go through the same process of multiplying the width times the height, which is determined by the function value. Okay, so on the first one, the base is of length 1. The height is f of 1, which is 2, right? F of 1 is 2, so times 2. Plus, the base of this rectangle is 3 times the function value, which is also 2, because we're here, right? F of 4 is 2, and that's what I'm going to be using. On the following rectangle, the base is 1. The height is determined by f of 5. f of 5 is 4. So 1 times 4. Plus the last rectangle, the base is 3 times the function value at 8. F of 8 is 4, so I multiply that by 4. And then again, I multiply and add, and that is the approximated value. So we have 2 and 6, that's 8, and 4 is 12, and 12 is 24. Did I do that correctly? 12, 16, 22, 24. All right, so look, in this case, so notice, so what's the error in this approximation? We didn't include this piece. We include this here, which shouldn't be there, this little piece, and we didn't include this, and we did include this part, which doesn't go, right? However, well, that's an approximated value, right? So what I just illustrated is what we are gonna call the left Riemann sum and the right Riemann sum. Okay, that's the name of those. In this particular case, for both of them, we have a partition that is uneven, meaning the bases are not the same length, right? Okay, so how do you think we could improve these approximated values in each one of the two examples that we just did?
Use an antiderivative.
Well, to approximate it, we're going to need the antiderivatives. That's true. But if you were to improve this approximation, what would you do? What could you do? How could you, for example, eliminate the fact that this piece was not included, or this piece was not included, or that we actually included something that shouldn't be there? What do you think you could try to improve this? Any idea?
Negative.
Negative.
The way to do, I mean, if you're given the equation of the line, you can just find the integral of the line. Like if you integrate, that's basically the area under the line.
Right, that's where we're heading. That's true, that's where we're gonna get, okay? But what could you do here to improve this approximated value? Well, what about if we make these intervals smaller? If we make the intervals or the subintervals smaller, meaning if we divide this into more pieces, then we are going to reduce the amount of area that we don't include and the amount of area that we include by error. By that I mean, this has a base of 1. But what about if base of 2? What about if instead of base of 2, I take a base of 1, right? So notice, just in this rectangle, in the first rectangle, if that was the case, and I will be using the left endpoint, right? This stays the same. This rectangle stays the same. But on this rectangle, if I use the left endpoint, then look, now my approximation is gonna get better because I already included this piece that I did not include before. Does it make sense? So same thing here. If the subintervals are of length 1, right? And in this case, in this particular case, if I consider this rectangle, look, I'm including stuff that I didn't include before. All right, so the idea is that if the partition is bigger, meaning we have more subintervals, this approximation will be what? Better, okay? That's the whole point. All right, so look, this is then where we're heading. It says rectangular approximation method of or Riemann sums. So suppose we want to know the area. So in this case, the exact area, right? Of the region bounded by this curve, the x-axis, the line x equals a and x equals e as shown in the right. The first step is to divide the interval from a to b in subintervals. We can then draw rectangles using the width of each subinterval as the base. Height of each rectangle is determined by the function value at the point in the specific subinterval and can be determined using 3 different methods. We only discussed 2, but there are more than 3 actually. So one of the methods is the left Riemann sum that I illustrated, the right Riemann sum, or actually we can determine that by the midpoint of the subinterval, okay? And each method in a way has his advantages over the others, right? Which one is more accurate? It really depends on the shape of the curve, okay? So, any question up to this point? No? All right.
No.
So moving forward. So here on example 1, I'm sorry, says with which rectangular approximation method is shown into the graph? Left, right, or midpoint? Look at the graph. Which one is used to in this illustration?
Left is used in the first one.
Left is used on this one.
The midpoint for the other one.
And the midpoint for the second. So it's based on what values you use to determine the heights of the rectangles, right? In this one, we use these points. Notice, if you're using the left Riemann sum, I don't use the last point. I start from 0 and end up here. I don't use the last endpoint. In this case, if I use the midpoint, then this is what is giving me the heights of those, okay? All right, so example 2 says the total area under the curve then is approximately equal to the total area of all the rectangles. Which of the graphs above gives a better approximation of the area under the curve and why? So which one is a better approximation? That or that?
The midpoint,
Why?
because there's less, it fills up more space of the graph. Or maybe not.
No, that
Because
is,
it overestimates.
it has less gaps, let's put it that way. And even though it does go over, probably it's gonna be less than if we, the error will be less than here because we're leaving more space out and we're really including this big jump, okay? So the midpoint, there are less gaps, and I would say leading to a smaller error, okay? So, summary of this process. Divide or partition the interval into n subintervals. Now, most of the time, we're gonna use intervals of the same length, okay? So I'm gonna introduce that here. If you have the interval from A to B, then the subintervals, the length of each subinterval is gonna be B minus A over N. So if you're doing this in n subintervals, then to guarantee the same length, you take the length of the whole interval and you divide by n. That is what we're gonna know as the delta x, the change in the x value. Okay? So create n rectangles with whose base equals the width of the subinterval. So in this case, they're gonna be equal to delta x, and whose height is determined by the function value, either at the left endpoint, right endpoint, or midpoint of the subinterval. And then you find the area of all the rectangles and then add them together, all right? So look, I know here it says 5 rectangles, okay? But from 0 to 8, I won't have 5 rectangles of the same length base, all right? So instead of 5 rectangles, I'm gonna take 8 rectangles, okay? So that means the following. So if you look at the first graph, we go from 0 to 8, right? So the interval is from 0 to 8. So my delta x is gonna be 8 minus 0 over 8, because I'm saying 8 rectangles. So each rectangle has to have a width of what? 1, all right? So that means that this is my first rectangle base, that, all of this, right? All of them have a length of 1. So on this one, I'm gonna use the left endpoint to approximate this with a rectangle. So I'm gonna use the left endpoint, all right? So I'm gonna draw my rectangles. So that's gonna be 1, right? I start with the left endpoint. This will be the next one. This will be the next rectangle. This is the next rectangle. Remember, I'm using the left endpoint to determine the heights. So on this one is gonna be this here. For this one is gonna be that one. And for this one is gonna be this here. So these are my A rectangles, okay? So how do I determine the area of each rectangle? The base times the function value, right? So for the first rectangle, it's gonna be, the base is 1, so it's 1 times. The function value will be f of 0, because I'm using this left point, right? For the second rectangle, the base is 1, and the height will be f of 1, plus 1 times f of 2, plus 1 times f of 3, plus 1 times f of 4, plus 1 times f of 5, plus 1 times f of 6, plus 1 times f of 7, and that's it. Because I go up to here, right? The left endpoints, I'm marking them in each subinterval, and that's it, right? I have 1 minute to finish this up. So you're going to estimate those function values. Some of them are not that, they're easily to estimate. But look, what is that we're doing here? This is a constant, right? So I could think of this as follows. 1 times, because 1 is the constant, right? Times the sum of f of xi, where I represents the subinterval. How many subintervals do I have? 7, right? 1, 2, 3, 4, 5, 6, 7. I'm sorry, 8. I'm using 7 points because I'm using the left point. So I, from 1 to 8. This f of xi represents the left-hand point. All right? Now, how do we calculate this? What is that one represents? Delta x, correct? So this really is delta x sum I from 1 to 8 of f of xi. Or I'm gonna write this delta x inside the sum. so you can see something. F of x, I, delta x, right? It's the same thing. So, and this is 8. So remember what I was telling you earlier, that the goal is to be able to divide this in a small subintervals to be more accurate, right? What happens if instead of 8, and I'm gonna finish with this, what happens if instead of 8, I have infinite many? So what happens if instead of 8, we have the sum I from 1 to infinity of f of x, I, delta x? What do you think we're doing?
Well, you're approaching the real area.
I'm approaching the real area. This is like a limit because I'm making very, very, very fine partitions, okay? This sum, and that's gonna be the topic of the next class, this is gonna lead to the exact area, okay? And we're gonna stop there for today. But that's the idea. We started with an approximated, then we figured out a method. How do I get the exact area? Well, this sum, when it goes to infinity, is gonna lead to that exact area, all right? That will be the class for today. Remember, we have a quiz next class.